So I'd like now to introduce Professor Dorian Garrick, who's a Professor of Animal Breeding and Genetics. Dorian previously held the J. Lush Endowed Chair at the Animal Breeding and Genetics at Iowa State University. Now, just a bit of history here. J. Lush is considered the father of modern animal breeding and was one of the first to teach the importance of selective breeding. He wrote his first textbook on animal breeding in 1937. Dorian began his research career at Massey University after graduating with a Bachelor of Agricultural Science degree with first-class honours. In 1994, Dorian was named to the Al Ray Chair at Massey University. Al Ray earned a doctorate at Iowa State University in 1950, where he was a graduate under J. Lush. So what a great New Zealand connection with Iowa State University and some important history in animal breeding. Currently, Dorian is the Chief Scientist at the Al Ray Centre of Massey University. Dorian has been involved in the development and implementation of the National Animal Evaluation Program's performance recording databases and breeding schemes. His recent work has focused on the theoretical and applied aspects of using genomic information to predict performance. Areas of expertise are genetic improvement of populations, genome-wide association studies, and genomic prediction. I will now let Dorian talk us through single step and the value it delivers to breeders and farmers. Dorian.
Okay, thanks, Matt. Okay, well, thanks for the opportunity to come and tell you a little bit about single step. So single step starts off with an equation to describe performance. And you might think of performance being breeding plus feeding, or if you're a little bit more technical, you might say phenotype is genotype plus environment. But from an analytical point of view, we go one step further and we write down what we call a linear model, which describes our phenotype. That might be a weaning weight, say, or a fleece weight, due to some environmental effects, like, say, the flock and year effect, maybe the age of the dam, depending on the trait, perhaps the sex of the lamb, maybe the birth rearing rank. And then there's the piece that you're interested in for selection, the breeding value or BV. And then there's everything else we can't explain, which we refer to as the residual. So that's the kind of model equation that has been fitted in all the analyses, going right back to the old National Flock Recording Scheme, Sheep Plan, Animal Plan, and so on. So conventionally, this breeding value part here has been estimated by taking account of pedigree-based relationships among the animals in your flock. But the big revolution about this breeding value took place in 2001, where Ben and a couple of his colleagues suggested that actually you could partition the breeding value into a part here that was explained by markers. So they said if we knew the genotypes at many of the loci that affected a particular trait, and that's what's in that M matrix, the marker values, and if we had these alpha vector, so that's the effect of each of the genes that you have markers for, if you sum up the effects of all those genes, you get a genomic breeding value. But the genomic breeding value, we wouldn't normally expect to totally explain the breeding value, because there could be some parts that maybe we don't have markers nearby, and the rest of it we would put into something which I often refer to as an extra polygenic effect, or EPE. So really our model equation for a breeding value has a part that can be explained by markers and a part that can't be explained by markers. So right now, you have in the past been estimating this from pedigree, but now we have the opportunity of estimating part of it using markers. So the two-step kind of methodology that's been commonly used in the past and is still commonly used in some industries, Andrew talked about an island for instance, this part here is calculated in one particular analysis, and then this piece here is kind of left out of it. So to get the most accurate breeding value, you have to blend these two pieces together. So in a two-step analysis, you do one analysis to get this marker part, you do another analysis to get the part you can't explain by markers, and then somehow you put the two of those back together again. So a single-step analysis fits both of those pieces in the same analysis. And there are lots of different ways of doing it, but one way to do it is to calculate genomic relationships rather than pedigree relationships of the animals with genotypes, and then have another part that can't be explained by markers. And that's known as single-step GBLUP, which you've heard about a couple of times today. So PBLUP we often refer to as pedigree-based BLUP, where we're using pedigree-based relationships. GBLUP, where we're using genomic relationships. Single-step GBLUP, where we do these two things in the same analysis together. And then there is another kind of single-step, which you haven't heard yet, called single-step Bayesian regression. And in single-step Bayesian regression, we actually fit the marker effects, just like Ben Hayes and his colleagues suggested back in 2001, and we add the extra polygenic effect, and we get the same breeding values as you would for single-step GBLUP. So there's more than one kind of single step out there. And I do have to declare here a conflict of interest. I actually only work 60% for Massey University. I have a company that works in the development of software for these kind of activities, and I have 2 full-time colleagues who work for that company, and we market the software to various people around the world in chickens and pigs and dairy cattle and beef cattle. So one of the questions you could ask is, what proportion of the breeding value can be explained by markers? If all of it could be explained by markers, we wouldn't have to worry about that extra polygenic effect, and then we wouldn't have to do any blending at all. There are some scientists who believe that we might get to 100%. I know Teo Mewison, one of Ben's colleagues on that original paper, believes that's the case, or has said that in the past. But currently, with huge data sets, in my experience, we seldom get to more than 70%. Now, what that means is if you do an analysis using only those marker effects, any widely used sires will not have the same prediction from markers that they got from progeny testing. And that's exactly the problem that the Irish saw when they tried to apply 500,000 animals genotyped using single-step GBLUP. They found that some of the widely used sires had predictions which were quite different from progeny test. And breeders found that uncomfortable, so that's why they went back to a 2-stage analysis. But we want our EBVs to be as accurate as possible, so what we do is blend these things. And in order to blend them, we have to work out how much weight to put on the molecular prediction and how much weight to put on the other piece from the data. So the 2-step approach, we compute the marker effects from historical data, we use the marker effects on newly genotyped animals, we compute information from pedigree relatives, and we combine them together using a selection index. So in order to define a selection index, we need to have an equation that describes the pieces that go into it, and then we have to have something that explains about the dispersion or the variation and the covariation. So this is the variation and covariance between the errors made in the pedigree prediction and the errors made in the marker prediction. And from that, we can work out the variance, covariance between the estimates of breeding values from pedigree and the estimates of breeding value from markers. And this part of the matrix here is used in the selection index methodology, which was invented at Iowa State in the 1940s and has been the basis of the National Flock Recording Scheme and sheep plan and so on. And when I was an undergraduate, we had to know how to set up and solve these kinds of equations for animals which had weaning weight, live weight, fleece weight, and NLB, and that's how we did sheep plan kind of analyses. But if you go through that selection index exercise, you can show that the breeding value, the new breeding value using all the blended data, comes from the breeding value from pedigree plus the breeding value from markers weighted by the accuracy of the pedigree estimate and the correlation between the marker prediction and the true breeding value. And you can similarly work out what the reliability of those breeding values are. So those are the equations that are used behind the scenes nowadays to calculate blended predictions, and that would be the case, for instance, in Ireland. Now, if you play with that formula, you can work out what the EBV accuracy would be from pedigree here versus the EBV accuracy from a blended such as a single-step analysis. So the black line there is just the line if there was no improvement in accuracy. The blue line represents what the single-step accuracy would be if the correlation between the marker predictions and the breeding value was 0.3. And if you square 0.3, you get 0.09, so that would be like having a marker which explained about 10% of the variation in the trait. So not a particularly good marker, but the kind of correlations we often get from data when we don't have a lot around. And I think Michael's examples had 0.4 there in the last slide. So what you see is that blending here makes a big difference if your animals have very low accuracy. But if you have a reasonable accuracy already, the blending doesn't actually help you at all. The marker information does not help an accuracy of an animal that already has a reasonable accuracy. But the more accurate we can get those marker breeding values, the bigger this lift is. So now if I go up to a genetic correlation of 0.64, if I square that, I get 40% of the variation explained by the markers. And now you see a much, much bigger lift for lowly accurate animals. And even reasonably accurate animals will get a lift from being genotyped. But one of the problems with this kind of exercise that you might forget is that when you get more accuracy, the animals are equally likely to have a prediction that goes up or a prediction that goes down. So when you come to market your animals, if you genotype them, you find that half of them are actually going to be worse than you thought they were before. And that might be sufficiently worse than they were before, because now they're very accurate, that they may not achieve the same price as they did before. So there are some value issues there about genotyping animals for sale. The other problem about that blending is that the equations for blending assumed an accuracy of the marker predictions, and I talked about a correlation of 0.3 or a correlation of 0.64, but it turns out that the accuracy is actually not the same for every genotyped animal. So whereas with conventional performance recording, if you observe a live weight or you measure a fleece weight, we can work out how much that will lift the accuracy of the breeding value or the accuracy of the index. When we genotype an animal, how much it lifts the accuracy varies from one animal to another. So often what you hear reported is kind of an average value, but some animals go up a lot more than that and some animals go up a lot less than that. The other problem with blending is that if you just re-estimate or recalibrate the marker predictions every so often, then suddenly those marker effects can have a big jump. And so suddenly you see GEBVs jumping just because a recalibration occurred. And we don't like seeing things jump, because when things jump, half of you call up about an animal that went down. I've never had a telephone call from somebody complaining about an animal that went up, but you all complain when they go down. So the solution is single step. We fit a joint model that either explicitly or implicitly includes the two components of the genomic enhanced breeding value, depending on whether you're doing single-step GBLUP or whether you're doing single-step Bayesian regression. There are many different ways to do it, and I'll just move on to the next. Two-step versus single-step. Two-step is really a misnomer. I've never done an evaluation which is a two-step. You know, we always have to clean pedigree data. We always have to clean performance data and cohort definitions. We always have to impute genotypes because a few, less than 1%, are missing on any genotyped animal. We have to do quality control, check that the sexes are correct, the breed is correct, the parentage is correct. We sometimes have to pre-adjust phenotypes. Then we do the calculation of the EBV, which is referred to as maybe two-step or single-step. But often we do separate analyses of different gold trait groups. So we do a number of different single steps or a number of different two steps. And then we have to calculate the accuracies, often from approximations. We have to error check form indexes and distribute the results. So whatever we do, it's a lot of work and it's a lot of steps. So how accurate is? Well, what was the value of single step is what I was asked. This is the best data we have that I'm aware of about the value of single step, or the value of genomic prediction. So this happens to be in layers, and this is a bit old now. Back in 2010, we were able to genotype several generations of layer hens. And this is the traits in layer hens. This is egg production, this is puncture score, yolk weight, albumin height, egg weights and egg colours. And on this axis here I've got accuracy, and the black line represents the accuracy of the parent average. And it goes up from the left to the right because I have sorted the traits here by heritability. And the heritability is the strength of the relationship between phenotype and genotype. So when the heritability is high, we do a better job of predicting genotype, which is what you see here with the black line going up. So that's conventional p-BLUP. The red line there represents our predictions of the next generation that didn't yet have any phenotypes, not based on parent average, but based on a genomic prediction, a single-step analysis using 3 generations of historical genotype data. And what you'll see is for all of those traits, we got more accurate predictions. That was a good thing. It wasn't the best thing. The best thing was the fact that we could actually do the selections now at 6 months of age. Laying hens start laying about 5 months of age, but normal selection doesn't occur till they're 13 months old. So not only did we get more accurate selection, we were also able to halve the generation interval. So that means we got much faster gains than we would have before. But the other thing that's a little bit unusual about this data set is we genotyped every mother and every father. So we could predict what the genotype of the offspring was if it had the average genotype of its parents. Now that wouldn't be a very good prediction of its genotype, but it's still a prediction. So the purple line there represents the parent average prediction using markers. And what we expected to see was a big difference between the red line and the purple line, because the red line has got the family effects and the differences between full sibs. The purple line has only got the family effects. And we expected those 2 lines to be very different. And to our surprise, what we found is that sometimes they're almost the same and sometimes there's a big difference. So what this tells us is that markers do a good job of picking up family effects, and sometimes they also do a good job of picking up differences of individuals within the same family. But it varies from trait to trait. And that's why it becomes very difficult to be definitive about the value of genomics, because we would say it varies. It depends on the trait, and we have no way of telling in advance whether we're going to have a new trait where the markers are good at predicting differences within a family, or they're mostly picking up these family effects. It's not just a simple matter of the heritability. And we believe that's something due to what we call genetic architecture or genomic architecture, which is a way of explaining we don't really have any idea what causes it. Okay, so the other cool thing about the chicken experiment was that traditional selection schemes for chickens, a nucleus had about 1,000 males and 3,000 females measured per generation, and of those, 60 of the 1,000 males were chosen to be fathers, 360 of the 3,000 hens were chosen to be mothers, and the generation interval was 13 months, and most of the measurements were on individual phenotype used in the pedigree BLUP. My colleague Jack Decker said, well, we can do a whole lot better than that. We can select them at 6 months of age, and we can get away with genotyping measuring only 300 male candidates and 300 female candidates, and choosing the best 50 out of 300 males and 50 out of 300 females. And we can do cross-classified matings. So if you know anything about chooks, they store semen, so you can't tell that who was the father of the egg just by knowing who bred the chicken most recently. So unless you genotype, you can't tell parentage. So normally here, one particular rooster is mated to 6 different hens, and each hen only gets mated to one rooster, what we call a nested design. So we do a cross-classified design. We get half the generation interval. And this graph here shows you, in the red line on the left, is the average phenotypic performance of the founder population before we started this selection experiment. And we ran this selection experiment for 3 years. So we had 3 conventional generations of 13 months each. And next to that, we had 6 generations where we reduced the generation interval to only half months. Okay? So 6 generations in sheep language is like about 30 years, which is probably most of your, or half of your lifetime performance recording. So this is a very interesting experiment. The yellow lines represent the performance of the conventionally selected population after 3 generations of selection. And you can see in most cases it's gone up. The green line represents the response of the genomic one, and you'll notice for all of those traits there, it's much better than the conventional one was, even though we greatly reduced the size of the population. So yes, genomic selection single step has a great advantage. It gives you much more accurate selection than parent average. But secondly, if you want to get the most value from it, you don't just do the same things you've been doing for years and add genotyping on top. You actually have to go back to the drawing board, use some innovation, redesign your breeding scheme, and in this case, you can get better gains and reduce costs all at once. Okay, so this is some other examples showing you single step against other methods in Hanwoo. So the Hanwoo beef cattle to South Korea is the same kind of thing as the Wagyu is to Japan. So it's a highly marbled breed, and they have central progeny testing. And here we have genotyped some Hanwoo animals, and the blue lines here represent single step G-blup. And there's 3 versions of it. This is the normal single-step G-blup where every marker is weighted equally, and the SS-G-blup 2 and 3 is where genomic relationships are recalculated using the markers with larger effects, which some people think does a better job. The green lines here are pedigree-based blup using all of the animals or using just the genotyped animals. And these orange lines here represent estimation where we only use the genotyped animals. We don't use any of the records from animals, any of the phenotypes from animals that are not genotyped. And the yellow ones represent when we do single-step Bayesian regression. So there's single-step Bayesian regression, and the blue is single-step G-blup. And you see for marbling, we got a significant lift for those traits, whether we did SSG-blup or single-step Bayesian regression. For eye muscle area, it turned out that actually we did a little bit better by only using the phenotypes on the genotyped animals. We don't quite understand why that is, but you can see the orange lines are slightly better than the blue or the yellow ones, but really no difference between the single-step Bayesian regression and the single-step G-blup. But then when we look at carcass weight, we see we got quite a big advantage from doing this single-step Bayesian regression. And the reason for that is that carcass weight had a few genes with very, very major effects. And when there are genes with major effects, we know that we don't get the best predictions by treating every marker equally. We do a better job by listening more to the markers that have strong signal and by assuming that some of the markers actually have a 0 effect. And that's a method which goes back to Ben's paper in 2001. And so in that case, the single-step Bayesian regression or the Bayesian regression where we use only the genotyped animals does a lot better than the SS-G-blup does. And doing this SS-G-blup iteration where you re-weight the genomic relationships did give an advantage. It still didn't give as good a result as we got from using SSBR. The trouble with doing this iterative re-weighted G-blup is that you never know in advance whether it's going to help you or not. So when you come to back fat, when you use that same method of re-weighting the genomic relationships, the predictions actually went down. So these are one of the reasons that I prefer the Bayesian regression kind of approach over the SS-G-blup kind of approach. Okay, so this is just something to show you about the genetic architecture. So this is a parameter pi which is the probability that a marker has zero effect. So when I say 0.6, I say that about 60% of the markers on the chip I don't think affects this particular trait. And then here we have 70%, 80%, 90%, 99%, and so on. So as I'm moving from the right to left, I'm assuming that many of these marker effects are not helping the prediction. And you can see for a lot of these traits, the prediction really doesn't change. So we don't really need the 50,000 markers. Maybe we only need 5,000. But once we start to getting to fewer and fewer and fewer, we start seeing the performance fall off. And that tells us that the genes for this trait are distributed right across the whole genome. So we need to fit lots of marker effects. But here we see the one for carcass weight, where the predictability actually went up by fitting fewer of those markers. So that's the kind of thing that we want to take advantage of. For those traits that have major gene effects, we want to capture them. Now, when you come to multiple traits in SSGBLUP, since you use the markers to compute genomic relationships, you use the same genomic relationships for every trait. But if you fit the kind of Bayesian regression model where you say some markers have zero effect, it's plausible that some of the markers that affect a trait like weaning weight don't affect a trait like fecal egg count, right? So it's possible to do a multiple trait evaluation where we have some markers affecting just one trait, some markers affecting just another trait, and some markers affecting both. And this is some results here, and the red line here represents the accuracy we get from a multiple trait model that allows the markers to be different for different traits versus a blue one here where we make the same markers be used for the genomic relationships in all of the traits. Okay, so the last comment I wanted to make is that if you're going to do these things, not only do you have to rethink the way you're doing your selection, not simply do everything like you did before but add genotype, you also have to exploit the extra accuracy with sensible selection. And so this is just coming back to first principles. This is a paper from Patrick Morrell and Paul Kenyon in the New Zealand Society of Animal Production. It's based on a Manawatu farm, a sheep farm based on a number of years of real data, but fitted to a simulation model, real grass growth curves. This is the farm gross margin in dollars per hectare. And along this axis here, they've got the body weight, the mature body weight of the ewes. And on this axis here, they've got the prolificacy or lambing percentage. And so here you have this kind of three-dimensional graph that's a little bit hard to see. But if I fill out one of those lines in blue, that is a 65 kilo ewe, and you can see that as the lambing percentage goes from 140, 160, 180 up to 240, the gross margin per hectare goes up. So selecting for higher reproductive performance, if body weight is held constant, is going to be good for you. On the other hand, if you were to have 150% lambing and you could select to reduce the body weight of your ewes from 75 kilos to 65 kilos to 50 kilos, you'd get an increase in profit because you'd be running more of those same lighter ewes on the same farm. This farm was optimized to use the same amount of dry matter in all these examples. But lastly here is a line where the profit doesn't change, and this is a line where the ewes get bigger and the lambing percentage goes up at the same time. Now you could argue about the fine points of this particular paper, but these were the values here where their profit was the same. So going from a 60 kilo ewe with 180% to a 70 kilo ewe with 144%, the profit actually didn't improve on that Manawatu finishing system with constant dry matter. And the reason I put this up there is that people vary in the extent that they believe in breeding values and indexes. So you might do all the recording, you might get all the indexes, you might rank the animals, but you have two animals of the same index value and there's one bigger than another. You might prefer to take the one that's bigger than the other because maybe the ram buyers are preferring to buy the ones that are bigger than another. So it's quite possible, even though the indexes that Abacus Bio and others have developed should ensure that you increase profitability, if you impose your own selection on top of those indexes, you can actually give away a lot of the financial benefit you might otherwise get. So Genomic prediction, it does add costs. You've got to genotype animals. Phenotypes are still required, but it does add accuracy that can accelerate genetic gain, but only if you take advantage of that extra information. The benefits vary from trait to trait, and they are best for traits that are not measurable on the individual by selection age. So it's not going to do much for you for weaning weight, live weight, and fleece weight if you're recording all of those phenotypes by the time you do the selection of animals as parents. The best value proposition is when it's used for nucleus ram selection rather than for evaluating sale rams. So driving your genetic gain, which is automatically going to flow through to your ram buyers over the successive years. The greatest value from genomics, I said it will require different breeding schemes from what you're running now, and single-step methods are preferred over two-step methods as they use all the data in the same analysis. Thanks.
Thanks, Dorian. How's everyone's minds?
It'd be a brave man that asked the question.
Yeah. Who's the brave person?
Dorian, I really thought when we had genomics coming up that that was going to be the end of me having to objectively measure. What you've just told me is that that's not going to happen. And at the very best, we're looking at 70% accuracy from a straight genomic measure. Is it likely, give us a time frame, is it likely we're going to get up around those 80 or 90% so that we, in theory, could not have to objectively measure?
I doubt very much that we're going to see it a lot more than 70, perhaps 80%. It's different if we're talking about a simply inherited trait. So anything that's got one or two major genes, you may be able to do a good job of predicting that major gene effect. But any trait that's controlled by a number of small genes, it's going to be much more difficult. And one of the reasons for that is that the breeding value is, an animal doesn't have a breeding value that applies in any and every environment. An animal's breeding value depends on the gene frequency of the animals it's mated to. So an animal's breeding value is actually different in different breeds. It could be different in different environments. And when we do a normal progeny test kind of evaluation, those things are taken into account because the progeny are telling you what the value of that animal was in that particular circumstance. When we use these markers, if you're trying to predict what the value of this animal is in every circumstance, you can't be accounting for those gene frequency differences very easily.
Thanks, Dorian. I'm just mindful of time. If you could just put your hands together for Dorian, and also we'll take a couple of minutes to stand up and just stretch our legs.